Hi everyone. In today's lecture, I'd like to talk to you about heat capacities for ideal gases. In a previous lecture, I talked about the heat capacity for solids and liquids, so if you need that introduction, you can go back and watch that in a separate lecture. But for now, moving on, let's talk about ideal gases and the heat capacity. Remember, the heat capacity is defined as the amount of energy that it takes to raise the temperature of a substance by a certain amount delta T. We generally use the symbol Q to talk about the heat energy that has to be transferred to a substance like an ideal gas to raise that temperature by some amount delta T, and then we use C oftentimes for the symbol for the heat capacity. Now, if you're talking about an ideal gas, you've got a lot of different processes that can change the temperature, right? So you can add heat to the system, you can do work on the system, and either one of these things could, or both, some combo, could change the temperature. Now, if the change in temperature is the same for a given set of processes, then that means that the change in the internal energy of the gas would also be the same. So the heat could be different for different paths that lead to the same temperature. Here in this diagram, I show two isotherms, one at a temperature T and one at a temperature T plus delta T. So we could assume, for example, that one of these curves, the bottom curve, for example, is at, say, room temperature, and then the other one is, say, boiling point of water above room temperature. If you were to take the gas from 293 to, say, 373 Kelvin, you could do it by any one of these orange paths, starting out at the initial point and ending up at the final point. And since the temperature of all those different paths ends up at the same temperature, that internal energy change would be the same. But if you take it on the different paths, you're going to have a different change in volume, for example, as you can see. The final point F, F prime, and F double prime, see, each one of those is at a different volume, right? Even if they all end up at the same temperature. Now, since we know that the work is proportional to the change in the volume, then that means that the work is not going to be the same for any one of those three paths, right? Well, if the work isn't the same, then that means the heat also must be different to arrive at the same final internal energy, okay? So, the heat and work associated with a particular change in temperature is not unique, even if delta U, the change in the internal energy, is unique. Now remember that we talked about a heat capacity, C, equaling to the heat energy that it takes to raise a substance by some delta T. So C is equal to Q over delta T. So this is the full heat capacity, not the specific heat, by the way. All right? Now, via the first law of thermodynamics, delta U, the change in the internal energy of the system, is equal to the sum of the heat and the work. So we can rearrange this expression and solve for Q. And Q would then be equal to delta U minus W over delta T. So you can see here that as opposed to what's going on for solids and liquids, you can have a very different kind of numerical expression here, depending on whether you have work or you don't have work for that gas that's being done. If the work changes, that's going to change your heat capacity. Now, this is different because solids and liquids don't expand a lot as they're heated. So remember, those coefficients of expansion, thermal expansion, are generally pretty small numbers. So that means that solids and liquids don't expand tons compared to gases. And because gases do expand a lot, more than solids, gases have to be treated differently. Now, there's kind of an infinite amount of steps, ways to get from one temperature to another temperature. We can't, in reality, define a heat capacity for all those paths, but what we can do is define heat capacities for two processes that frequently occur. And remember, this isn't going to cover all processes, okay? So we can talk about constant pressure processes, and we'll call those C sub P for heat capacity at constant pressure, or we can talk about constant volume heat capacities, so that's C sub V for capacity at constant volume. Now we can also use the number of moles N and define molar specific heats for those processes. And so now I'm going to take you through the mathematics of what's going on with that, okay? So remember that our expression for the heat for a solid or liquid was Q is equal to mc delta T, m times little c times delta T, where m was the mass and C was the specific heat, and then delta T was the change in temperature. So our molar specific heats look very similar to that, okay, except now we're going to use the number of moles and then the heat capacity at constant volume or constant pressure in those expressions. So for constant volume, our molar specific heat expression will be Q is equal to NC sub V times delta T, where N is the number of moles, C sub V is the molar specific heat at constant volume, and delta T is the change in temperature. Note that for constant volume processes, since the work is proportional to dV, that means that if the volume doesn't change, the work is zero. We covered this in a previous lecture. Now, at constant pressure, we have Q is equal to N times C sub P times delta T. And here, again, N is moles, C sub P is heat capacity at constant pressure, and then delta T is that change in temperature. For constant pressure processes, we derived this expression in a previous lecture. The work is equal to minus the pressure times the change in volume, minus P delta V. Now, you'll note that these are going to be different. The constant pressure heat, that has to account for both the increase in the internal energy and the transfer of the energy out of the system by work. So when ideal gases have an increase in temperature at constant pressure, they're going to expand. Okay, so this has to count for that. So let's talk about the math of that. You're going to have a heat for constant pressure that's going to be greater than your heat for constant volume for given values of N and delta T, moles and change in temperature. So showing that, Q is equal to N times C sub V times delta T. Now, Q here is going to equal to delta U because the work is equal to 0. But for constant pressure processes, Q is equal to N times C sub P times delta T, and that is going to equal to the change in the internal energy delta U plus P delta V, because you see Q would be equal to delta U minus the work, and the work is minus P delta V, so minus a minus is a plus. So Q will be equal to delta U plus P delta V, okay, for constant pressure processes. Now let's solve. If we're talking about a per mole basis, so this is for N equals to 1, then using that expression that I just derived on the previous slide, I can solve for C sub V for constant volume. C sub V is going to equal to Q over delta T, which is delta U minus W over delta T. And now since W is equal to 0, that's delta U over delta T held at constant volume. Okay, constant volume. Now, if we take a small delta T, so we take the limit as delta T goes to small values, then this ends up being the derivative of the internal energy with respect to the temperature holding volume constant. Okay, so we have partial U with respect to T holding volume constant. The partial is to take care of only the explicit dependence on temperature here and ignore any, implicit changes. And remember here we're holding volume constant. Okay, now let's talk about a monatomic gas like helium. In a previous lecture on equipartition of energy, we derived the expression for the internal energy of an ideal gas. And that is U is equal to 3/2 big N kT, where big N is the number of molecules, K is Boltzmann's constant, and T is the temperature. But I could also write that as 3/2 times little n RT, where little n is the number of moles, R is my gas constant, and T is the temperature. Now remember here we're talking about a 1 mole basis, so N is equal to 1, so that means that U is 3/2 RT. So since I have this expression for U, I can now take that derivative of the internal energy with respect to temperature holding volume constant. If I do that, the derivative of 3/2 RT with respect to T is 3/2 R. Okay? Now my gas constant in SI units is 8.314 joules per moles Kelvin. So, rounding to 3 significant figures, I end up with C sub V is equal to 12.5 joules per Kelvin for 1 mole of an ideal monatomic gas. Now let's look at the constant pressure expression. Okay? Remember, C sub P is equal to Q over delta T. Plugging in for Q using our first law of thermodynamics. Q is delta U minus W, and then we divide that by delta T. Okay? Remember that this is for constant pressure, so this is holding pressure constant understood right here. Now, if I shrink my deltas, right, shrink them down to small values, then what I end up with is delta U over T plus P delta V over delta T. And then taking that to small values, that ends up being the derivative of U with respect to T, holding pressure constant, plus P times the derivative of the volume with respect to T, holding pressure constant. All right? Now, we already talked about what the derivative of U with respect to T is, right? But what's the derivative of V with respect to T? Well, this is for ideal gases. And so if we use our ideal gas law, V is equal to nRT over P, okay? Now, if we take the derivative of that expression with respect to T, holding P constant, right, then we end up with nR over P. Now, this is for 1 mole, so N goes to 1 here, okay? So here we have Cp is equal to 3/2 times N times R, which would be 3/2 times 1 times R, plus nR over P times P, don't forget there's a P out front, P times partial V with respect to T, and that gives me nR, N is 1, and so that's 3/2 R plus R, which is 5/2 R. Now plugging in for our gas constant, 8.314 in SI units, we end up with a heat capacity at constant pressure of approximately 20.8 joules per Kelvin for 1 mole of an ideal monatomic gas. Now if we compare that to our value for C sub V, right? Remember that C sub V was 3/2 R. So if we take C sub P minus C sub V, that's R, okay? So that's something notable. Now, this is actually a theoretical prediction that's in pretty good agreement with the experimental results for monatomic gases. I'll show you that in just a second. Now we can also define our constant gamma, which was introduced in a previous lecture. Gamma can now be defined as the ratio of the molar specific heat for constant pressure processes divided by the molar specific heat for constant volume processes. So that would give us, for an ideal monatomic gas, 5R over 2 over 3R over 2, which is 5/3, or about 1.67. Now remember, in the lecture on adiabats, we talked about the adiabatic exponent, gamma. Gamma was F plus 2 over F, where F is the number of degrees of freedom that the gas has, okay? So for a monatomic ideal gas, F is equal to 3 because it can move in the 3 translational directions. So that would be 3 plus 2 over 3, which is 5/3, okay? So this is another way to express that, okay, the adiabatic exponent. Now, if you look at the theoretical values of C sub V, C sub P, and gamma, they're all in excellent agreement for monatomic gases, but they're in serious disagreement with the values for more complex molecules. And this is because the internal energy of more complex gases must include contributions from rotational and vibrational motion of the molecules. In other words, for monatomic gases, like helium, for example, it can move in 3 directions, but that's all the degrees of freedom it has. But if you have something like diatomic nitrogen, right, which is, a lot of what you're breathing right now, you have 2 nitrogen molecules side by side. And so if you think about what that could do, the nitrogen molecule could rotate in 2 directions, right? Or the nitrogen atoms could vibrate about that bond, and that might give them more degrees of freedom. And so F isn't 3, okay? Now, in the cases of solids and liquids heated at constant pressure, very little work is done and the thermal expansion is small, so C sub P and C sub V are approximately equal. But gases, they're different, okay? So that's why this is a breakout lecture. So we've got a translational motion, that's 3 degrees of freedom, like monatomic ideal gases. If you're talking about a diatomic gas like nitrogen, that can add 2 more because it can rotate about 2 axes. Vibrational motion, that would add 2 more degrees of freedom to it. And so we would have U is equal to 7/2 nRT, and then C sub V should be 7/2 R, which is 29 joules per mole Kelvin. But that doesn't match our experimental results. Like carbon monoxide at room temperature is 21 joules per mole Kelvin. So let me just show you some of these results here in this slide, okay? So you can see the monatomic gases, they're in really good agreement. Remember I said C sub P should be about 20.8, and it is for helium, argon, neon, and krypton. C sub V should be about 12.5, and it is pretty much. There's a little deviation there, but it is pretty much. C sub P minus C sub V should be R, and it pretty much is for these monatomic gases. And gamma should be about 1.67, and it is. So our monatomic gases, very good experimental agreement. But not so much here, okay? Not so much the diatomic, okay? You can see that they don't match the theoretical predictions quite as well. And then if you go to polyatomic, it gets even worse, okay? The discrepancies get even worse. So what's going on? Okay, what's going on? Okay, well, here's what's really going on. Your molar specific heat is actually a function of temperature. Now, at low temperatures, your degrees of freedom get frozen out, okay? So this is a plot, for example, for what might happen to a diatomic gas like nitrogen. Now, at very low temperatures, say 100 Kelvin or below, a diatomic gas can actually act like a monatomic gas. In other words, it's not going to be able to rotate or anything. It's just going to move in 3D, and that's that. Now, once you increase the temperature to room temperature, say, roughly room temperature, then those rotational degrees of freedom get unlocked. And then at room temp, you have pretty good agreement there with the rotational degrees of freedom. But you're not going to see the vibrational degrees of freedom until you get above 1,000 Kelvin, okay? Now, the reason for that is quantum mechanics, okay? So, let's show this energy level diagram. Quantum mechanics. Here's an energy level diagram for a little sketch, for example, for a diatomic gas like nitrogen, okay? What actually happens is that you have these rotational states and these vibrational states, and they actually have specific energy as shown here in these two equations. So you have rotational energy states that go like h bar squared times the quantum number for rotation j times j plus 1 divided by 2 times the moment of inertia, okay? And then the vibrational energy states, n plus 1/2 h bar omega, where n is the quantum number for that value, and then h bar is Planck's constant divided by 2 pi, and omega is the frequency of vibration. So see here, you have these equations from quantum mechanics that govern it. Now, if you were to draw out the energy level structure, this is kind of what it looks like right here. You get, as energy goes up, rotational states that are pretty closely grouped together, right? And then the vibrational states are actually separated by quite a bit, okay? So that helps explain why you have for very low temperatures, you see. Let's say that you're at very low temperatures. That means that you don't have a lot of energy. And at very, very low temperatures, you're not going to have enough energy to jump up from your ground state to that first rotational energy level. And so those rotational energy states are effectively locked out. You can't access them, okay? And so that means that those degrees of freedom for the rotational states are frozen. You can't access them. So it acts like a monatomic ideal gas. Now, as you increase in temperature, it's able to jump up to these higher level energy states in rotation. So that unlocks those degrees of freedom. As you increase the temperature, these become accessible until they're fully unlocked at room temperature, and you can access all these rotational energy states. But look at the big jump in between the ground state here and the first vibrational energy state. See, that's a lot more energy. And so it takes a lot more heat to unlock vibrational degrees of freedom than it does rotational degrees of freedom, okay? And so at high temperatures, like 1,000 Kelvin or so, those become available to you, and then those vibrational energy states become unlocked, and the molecule's free to vibrate, and then they can access that. And see, all that affects the heat capacity. So this is the idea that you have these heat capacities that you plot versus the temperature that change as the temperature changes. And the explanation for that is quantum mechanics, okay? Now, I don't care so much that at this point and at this level that you fully understand these equations here at the bottom. We're going to get more into those as we go further into this course, okay? For now, I just want you to understand how the increasing energy of these energy states, right, causes the different states accessible to you to change as the temperature changes. Okay? So that's all for now. That's all for this lecture. I hope you understood and enjoyed that. And as always, I'll see you in class.